Machine learning architectures operate at an overwhelming scale. Millions of data packets route through hundreds of layers, calculating probabilities in milliseconds. Strip away the massive server farms and the billions of parameters, and the entire structure reveals a framework of basic logic gates. At the computational bedrock, the system relies on a single binary node, evaluating one state, true or false. Before engineering complex AI models, a programmer must first define how Python categorizes raw reality into computer memory. We will build the architecture of Python execution from the ground up. This process starts with atomic data types, connects them through operators, and finally organizes them into automated logical loops. Understanding these mechanics provides the blueprint for how machines process and interpret data. To build our model, we must first lay out our raw materials on a conceptual workbench. The most basic units of data are integers, which represent whole numbers, and strings, which hold text representation. When a calculation requires decimal precision, we use a float. In Java, you manually define whether a decimal is a standard float or a high-precision double. Python consolidates all decimals into a single float category. This allows the system to process varying levels of precision without requiring the programmer to reallocate memory types. Python also includes native support for complex numbers, such as 3 plus 4j. Including complex numbers as a primitive type is a deliberate architectural choice. The memory block splits into two distinct components, a real number and an imaginary part used for calculations in advanced machine learning and electrical engineering. This leads us to the final primitive required for algorithmic execution, the Boolean. A Boolean serves as the arbiter of truth in a program, strictly constrained to one of two states, true or false. Right now, these primitive data types are inert. To create action, we need a mechanical force to evaluate them. We apply that force using operators. Arithmetic operators are the first layer, used to manipulate numbers mathematically. We can differentiate between standard division and floor division. While 4 divided by 3 yields a repeating decimal, floor division, represented by 2 slashes, slices off the remainder entirely to output a clean integer of 1. To bridge raw numbers and system logic, we use relational operators, such as greater than, less than, or equal to. Passing two primitive numbers through a relational operator collapses them into a Boolean state. The relationship is either true or it is false. To synthesize multiple Tempelchen simultaneously, we use logical operators, and, or, and not. To verify if 5 is less than 6 and greater than 2, it must pass through both gates to output a true signal. If we change the input to 7, the first gate fails, causing the entire AND logic chain to return false. The OR operator only requires partial adherence. If either side of the evaluation is true, the system proceeds. The NOT operator functions as an inverter. Without this space, the compiler cannot group the logic, halting the sequence with an indentation error. When an if condition is false, the system uses elif and else as backup paths to keep the program running. Visualized as a vertical stack of gates, the number 9 hits the top if gate, checking divisibility by 2. It fails, bouncing down to the elif gate for 3. This flashes green, letting the number pass and bypassing the else phonak. This conditional branching provides the mechanism for programs to react to unknown data inputs. Routing a single data point is useful, but modern machine learning requires processing incoming data at a massive automated scale. To automate this logic, we use a for loop to iterate over a dataset. The for loop relies on the range function to establish its operational boundaries. The range function uses 3 parameters: start, end, and step. A marker starts at 1, jumping in increments of 2, stopping before 11. Python's rule is strict. The starting bound is inclusive, but the ending bound is strictly exclusive. To print a multiplication table from 1 to 10, we must set the range to 11. The loop will process the number 10, but will stop immediately before reaching 11. The step value further optimizes this by allowing the loop to skip iterations when strictly sequential execution is not required. Implementing a for loop transforms a manual routing process into an automated assembly line, executing decisions thousands of times per second. This pipeline connects our individual components into a functioning logic engine. Primitives provide the material, operators generate truth states, conditionals route those states, and loops provide the scale. These interactions create the internal logic of the Python environment. Advanced artificial intelligence models rely on this same architecture, scaled up across millions of parameters and neural weights. Mastering these atomic mechanics moves a programmer from writing static commands to engineering automated logic engines. This is the foundation required for machine learning.